Hi everyone, you're welcome in my channel Creative Media and YouTube. This is my tutorial video. It's me Kusum. I'm at Mathematics, Kathmandu University School of Education. So today's our topic is reflexivity, symmetricity, and transitivity in relation. So by showing some example, I'm going to define these reflexivity, symmetricity, and the transitivity in today's class. So today's topic related to our this topic, we have some learning objectives like this. So at first to define a reflexive, symmetric, and transitive relations, today we'll try to know and understand this, and this way to understand the example of each of them. So I'll show some examples related to this, and next to know graphical representations of each of them by graph. So by using the graph and the directed graphs, I will try to know, and next I'll try to provide the real life examples of them. This way to identify equivalence relations and how can we establish and what properties should be there to be equivalence relations in a set. Okay, and now reflexivity, this is also the property of the relation. So here a definition: a relation R on a set A is reflexive if every element is related to itself. For example, like this set A, suppose we have set A with the elements 1, 2, and 3. Then if we establish the relations A to A, such as 1 comma 1, 2 comma 2, and 3 comma 3, like this, other elements, other R pair also will be there, like 1 comma 2, 1 comma 3, 2 comma 1, like this, 3 comma 1. So I have shown this special case, like if they have at least their own images as in other pair, the relation. So we can say they are as the what reflexive, or the what they have reflexive property in them. And the graphical representation, so in this graph, suppose point 1, 2, and 3 with a loop connecting each point to itself. So that's one example. So I have tried to show in the graph, like A itself has a loop. So that means A comma A, it means in this way A to B also connected here, directed toward the B. So A to B, in this way B also it has loop itself. So it is B comma B. In this way B to C, and the C itself has a loop, like here C comma C, again C to B also here. We can see this one. So in this way, a real life example, like here the equal is equal to relation. So it is here equal to, for example, 5 equal to 5, like 1 equal to 1, 2 equal to 2, and 3 equal to, like this. So we can see here in this example in this way. So now symmetricity. So for this definition, a relation R is symmetric if the A comma B, this order pair, belongs to R. Implies that B comma A also belongs to R, the real number. So it happens here in the example. Let's try to check in the example. Suppose we have set A, so with the element that is 1 and 2, then we can establish the relation A to A like this. In such a case, 1 comma 2 and 2 comma 1, and then 1 comma 1 and 2 comma 2 maybe here. So here we directed here at first 1 to 2, and it's inverse like order pair. So by exchanging their positions, 2 comma 1 has been written like this. Suppose if we mention 1 comma 1, then also itself it is what, like inverse. So the replaces the position like 1 comma 1, again replacing their positions, we can write 1 comma 1. Okay, for the graphical representation, 2 points with the bidirectional arrows between them. Suppose, let's check over there in this graph mentioned over here. Suppose here at first 1 comma 2 is here, and again 2 comma 1. So from 1 to 2 it is directed, the graph, and this way 2 to 1, like this. 1 comma 5 is here, in this way 5 to 1 also there, like this. We can check, these are some example, and here also the what that means bidirectional. Here we can check 3 comma 4, 3 to 4, and 4 to 3, like this. These are connected. So this here you can check 1 and 2 and 1 and 5, and in this way we can check 4 and 3, or the 3 and 4 are linked with the bidirectional arrow in the graph. Similarly, we can check here also A to B or the B to A. In this way, A to C and C to A. These are also the what bidirectional arrow. They have the relation like, and A to A, B to B, and C to C also themselves. Like in real life example, we can check here the is a sibling relation. So like that means like brother and sister. We can talk regarding that. So the brother is the sibling of the sister, or the sibling is the sister of brother, like we can take like this, is it? So that is the real life examples, and many more we can add. So explore yourself in this way. Transitivity now. So as a definition, a relation R is transitive if A and B or a pair belongs to the real number R, and B and C if belongs to the real number, same real number R, the relation R. That implies that A to C relation also belongs to the that order pair also belongs to the relation R, or the real number. So example, set A is equal to, suppose we have the element like these elements 1, 2, and 3. So that's A to A relation we can represent by R. So it is 1 comma 2 order pair, 2 comma 3 order pair, and 1 comma 3 order pairs are here. It means here. So we can show like this. Suppose 1 is 1 comma 1 and 2 are connected. Again 2 and here 2 and 2 we can check. Here 2 and 3, 2 and 3 also connected, so related. So in this case we can show like this. So 1 and 3 are also available in that relation, so it is the third one. So like this, 1 comma 2 and 2 comma 3 are given, so that it must be exist, that is the what existence of the 1 comma 3 also there. So this is known as the what is transitivity, for example, in the example. So graphical representation, we can say here 3 points with the directed edge are forming a chain. So here, so like this we can see, suppose here we can check here this B1 to B2, and then B2 to B3 has been shown as the edges, and that these are the what coordinate, and here the point, and B1 to B3 also exist. Let's see, okay, B1 to B2, again B2 to what is B3, so on. So this B1 directly it is directed toward the what is B3, so B1 comma B3 can be seen here. Likewise, the other example, suppose we can check here, suppose here B5, and B5 is directed toward the B2, again B2 is directed toward the B3, then B5 is directed toward the B3. We can write B5 comma B3. So we can say here, likewise B5 toward the B4 in this way, and B4 toward the B3. That's why here we can check B5 again toward the B3. This is correct for us. So like this we can check. Okay, for the next here real life example. So the is an initiator of the relations. So okay, so we can provide like this example, real life example. Okay, for the next, now properties of equivalence relations. Now we talked already regarding the what is reflexive, that means the element of any set if itself is what that means constructing in the relation, or the what creating the order pair of the what 1 with 1, 2 with 2, 3 with 3, then such type of relation is known as a reflexive relation. So in this way we talk today regarding this symmetric also, that means if A to B is existing in the relation as an order pair, then B to A also exists. So this is also that we discussed before. In this way, the third one, transitive. So if A to B relation is A to B relation, that means that means A to B order pair is existing in the relation, and the B to C also existing. If so, then A to C is also existing in that relations. So this is the transitive. These three, reflexive, symmetric and transitive, if properties, these properties are available in a relation, then we can say that is equivalent relation. What is that is known as what? Equivalence relation. So here, to be equivalence relations, reflexive, symmetric and transitive properties should be carried. Okay, as a summary, we discussed today the reflexivity, that is every element is related to itself, that is self-looped in the graph we discussed, and the symmetricity, if A comma B belongs to that order pair belongs to in relation, then the B and A, that's inverse of that one, also belongs to in the same relation. If so, then that is as a in a graphical representation we can show by the bidirectional arrows in the edge. In this way, transitivity, if A and B that means AB belongs to the relation, and the BC also belongs to that relation, then obviously AC also belongs to that relation. That is the what chain relationship, like before we discussed. And if these all the properties are seen in a relation, then that can be said to be a set equivalence relations, what we discussed before. Okay, thank you very much. I hope I try to clear the doubt, and obviously if in upcoming days I'll upload the videos related to this, so please try to comment and try to explore yourself. Thank you very much.